Hello to you from ChemHelp ASAP. We've learned about hybridization. It works great, and it does indeed, and we've applied it to second row elements like carbon and nitrogen and oxygen. But now, since it works so well for the second row, let's try to apply it to the third row elements and see how it performs. Okay, we have this nice table, and we're going to review a few molecules. So that the top molecule is ammonia. And ammonia, if we went through the number of attached atoms and lone pairs, we would find there are 4. And we would say, oh, of course, this is going to be sp3 hybridized. And the predicted bond angle for any sp3 atom is 109.5. And the experimental observed angle is about 107. That's a really good match. So that is a check. That works wonderfully. How about for water? We've already seen this example as well. 2 attached atoms and 2 lone pairs. Again, the sum of that is going to be 4. Excuse me. For hybridization, that's sp3. Again, our predicted bond angle is 109.5. And the observed angle is pretty close to that. It's 104.5. Everything's looking great so far. Now let's get down to our third row elements, and let's go to phosphorus. Phosphorus is right below nitrogen on the periodic table. It's in the third period and the third row. So again, phosphorus, just like ammonia, we have 3 bonds to hydrogen plus a lone pair. So we'd say, fine, that's A plus L equals 4. The hybridization we would expect would be sp3. The predicted bond angle, of course, would be 109.5. And then what is the experimental bond angle? 93.5. Wow, that is a big difference. Something is wrong here. How about hydrogen sulfide, H2s, our last molecule? Sulfur is directly below oxygen on the periodic table. It's a third row element. Again, if we did our usual counting method, 2 attached atoms and 2 lone pairs, it's a total of 4. sp3 hybridized, we would predict 109.5. What is our observed bond angle or experimental bond angle? It is approximately 92 degrees. That's not a good match. So somehow hybridization is failing, and this is a very limited sample size, but you can see it's failing on the third row elements, but it seems to work fine for the second row elements. As it turns out, hybridization is a predictive tool, and it does work very well in almost all cases for second row elements. But do not try to apply it to third row with other elements on the periodic table, because the value of prediction for hybridization, which is things like bond angles and geometries, it really doesn't work well outside those select few second row elements. Now, that's not a big limitation for us in organic chemistry. We deal with carbon and nitrogen and oxygen for the bulk of our molecules, so that's not a limitation. But outside of organic chemistry, hybridization is probably a less used topic, and because it's less useful, it has less predictive power.